Assalamu alaikum. We are going to do our 8th experiment. This is the final experiment, which is parallel operation of three-phase alternator. That is three-phase synchronous machines. Today we are going to put the synchronous machine in parallel with the electric grid. You remember in experiment 7, which we have given you, we connected the synchronous machine to a DC separated excited motor. This is the DC separated excited motor here, and this is the synchronous machine. And remember, we did the open circuit and the short circuit test. So now, this is the synchronous machine. This is its stator winding and the field winding. You can focus on the nameplate, and you'll see this is the nameplate of it: 380 volts, 1.6 amps, and then 0.6 field current. The synchronous speed is 1800 and frequency is 60. So again, we are going to use the DC motor to drive it up to 1800 and maintain it constant. Then we put on. Here, we are going to put two power supplies together. That is, our generator is going to be connected to SCICO. That is Saudi Electric. Saudi Electric comes from our panel and comes here. We have it here, three-phase supply: line 1, line 2, line 3. Each line is about 380 volts. You can see here, three-phase main supply to 80 volts. Now, here is it. This is my machine. The three lines are connected. One is connected through an ammeter, and the other is connected through a watt meter, and the rest are connected to a switch. This is the switch. This switch is connected to SCICO here and connected to my machine here. Now, this watt meter measures single phase because it's only one line, and the neutral comes to the neutral of the machine. So we are going to measure single phase power and multiply it by 3 to make it. For example, our machine is rated 0.8 kilowatts. 0.8 kilowatts. So if I am asked to put the machine, let the machine generate 50%, 50% will be 0.4 kilowatts. But that is three phase. This my machine, this my watt meter is measuring only single phase. So you divide the 400 by 3. So you get something like 133. So if you get 133 here, that is 400. You multiply by 3, that is 400. That is single phase. Now, how do we put the two machines to work? If we make a mistake, for example, this is SCICO. If I make a mistake and I switch, you see when I switch here, there's power here. If I make a mistake and switch here, I'll destroy the machine. You have to make sure that they run in parallel. What you mean by they run in parallel is one machine doesn't put power into the other. That is, they go together in one direction. How do we do that? We have conditions. The first condition is that the voltages should be the same. Line-to-line voltage of a machine that are connected to the line-to-line of the supply should be the same in magnitude. The same again, they should have the same frequency. That is the second condition. The third condition is they should be in phase, and the phase shift should be the same. Now, 4 conditions. How do we meet these four conditions? The first condition is that the voltages should be the same. We have a voltmeter here connected to the terminal of the machine. But if we use another voltmeter connected to the terminal of the supply, these two voltmeters, they have errors which are different, so we might get different value. So there is one unit which is called a double voltmeter. It has 2 voltmeters, meaning that if there's error, the error is for the 2 of them. So if we make the machines to run at the same voltage, if there's error, then the error will affect both, and then that way is the same. So what we do here is we connect the machine that is existing, that is the supply of SCICO, to voltmeter 1, and then we can see it is yellow and blue. From this line, that is line 2 and line 3. Line 2, line 3, and line 2. Since we use line 2 and line 3 to connect to voltmeter 1, we have to use our machine to line 2 and line 3 to connect to voltmeter 2. By using these colors, we are safe. We can know that these are the whole thing going on. Now, the frequency meter, also we have a double frequency meter that will read 2 frequencies. So we connect frequency meter 1 to the electric supply and frequency meter 2 to our machine. Since we already use this same line 3 and line 2, we connected line 2 and line 3 to from the grid supply to our frequency meter 1. Then line 2, line 3 of my machine here will be connected to frequency meter 2. We have here called sun scope. This sun scope is what tells you that the phase angle are the same, and it always matches when it comes to 12 o'clock. So again, the first one will be connected to the same line 2, line 3 and line 2 of the grid supply, and line 2, line 3 of my machine. Now here, to know the phase sequence, we have 3 lamps here. The 3 lamps are connected in a way. For example, look at the middle one. You can see that we have green. When we have this green, trace it and see this green up one goes to electric grid line 1, and it goes to my machine line 1. That means they are both. This lamp is connected to line 1 of this line 1 of supply, electric supply, line 1 of my machine. So if the phase sequence is correct, then it should be 0 because the voltage drop between these lines should be 0. So this line will go off, and this is called the dark method. We could have connected all the lamps that way, but we just want to make it add. Now look at lamp 2 here, this first lamp. You see that it is blue and green. It tells you that it is connected to 2 different lines. Blue and yellow. Look at blue connects to my machine electric supply line 2, and yellow connects to my machine line 3. That means it is connected between line 2 and line 3. So there is differences, so it has to come on. This is the bright method. The same way, this third lamp, yellow and green. Yellow is connected to line 3. It's line 3 of my supply, and then line 1 of my machine. So it is connected between line 3 and line 1. So what it means is that if the phase angle is correct at 12, we have to observe that the phase sequence should be correct. At that 12 o'clock, since we connected that the middle lamp should go off, it should be dark, and the 2 should be bright. So this is the combination method. Now, with this one in mind, we try to start our machine. Now, if we see that these lamps are not behaving that way, it means that there is a phase shift, and you have to connect the phase sequence is not correct. Now, first of all, we can start our machine. Start it. We are starting it by our DC motor, which is separately excited. Switch it on. It start on. We take this is our meter, which we can use to adjust the speed to 1,800. Now it is 1,103. So he's going to vary the speed to 1,800. Okay, it's okay. A little above 1,800, no problem. We'll leave it that way. Okay, it's okay. It's okay. Colors. A little above that. Now this machine is running at this. We can now use the field current. We can use the field current now to generate voltage. But before that, let us make sure we switch on Skiko here. Now we have seen that the power supply is 400. This switch is called the synchronizing switch. If we don't get everything correct, we mustn't switch this on. So first of all, we build up our machine to generate like we did in Experiment 7. No load test. What do? We increase the field current of the machine so that the voltage will increase. So before the synchronization, the field current will control the voltage, and we can see the voltage is increasing. This is before we synchronize it. We control the voltage with the field current. Let me repeat again. Before we synchronize, the field current of the synchronous machine is used in controlling the voltage. So we control the voltage up to rated, so that we can see that they are all the same, 400, 400. Then we come to look at the speed. Now, our machine is running far. This is the Skiko, 60 Hz. Our machine is more than 60 Hz. And you can see that the synchronoscope is running fast. So we use our DC machine to control the speed. Look at it. If I increase the speed, before synchronization, I'll control the frequency by controlling the prime mover. The prime mover is the DC, the machine that drives the AC. So here, the prime mover is the DC. When I change the DC speed, I'll change the frequency. Now the frequency of my machine is very high, so I'll bring it down by using field control. I'll bring it down to 60. You can see it. Now, because it's perfectly at 60, this thing is not moving very fast. So we can make our machine to be a little bit higher. So look at it. Now, as it comes to here, the lamps are not the same. Look at it. At 12, all of them lamps. This should have gone off and this will remain, but it's not. So it means that the phase sequence is wrong. So if the phase sequence is wrong, you change the phase sequence of any two lines here. You remove this one, D, and change two lines here and there. Now look at it again. At 12 o'clock, these ones are on and this is on. So at 12 o'clock, you switch on. But let us try to reduce. Let's illustrate one thing. You see here the machine, my machine is running at a faster speed. So this one is going clockwise. Now, if we make it to run very close, it will now reduce. So you see it. Now at 12 o'clock, I can switch it on. Look at it, 12 o'clock, I switch it on. So now they are connected in parallel. So you can see that the middle one has gone off and the two are lamps on. So now they are in parallel. You can see the frequency are the same, 60. The voltage is the same. Now, if we come look at our meters, we have our watt meter here. This watt meter, it can read active power and reactive power. It has a voltage coil and a current coil that we can set to read both of them. Now we can also look at it. If the machine is giving power, the positive lamp will lamp on. If it is taking power, the negative will lamp on. Now both of them are off, meaning that it is not giving power and it is not taking power. Now that means that at the point that we synchronize the machine goes into zero power. Look at this, P is 0, reactive power 2 is almost 0. So now if we have this one, 0 power, 0 reactive power. Now this is called perfect synchronization. We say that this machine is floating. It is floating because it's not a motor, it's not a generator. Now, how do we make it to generate real power? How do we make it to generate real power? That is, we put this one at P. If it is generating real power, this should come on and this meter should move here. That is to generate real power into the system. Now remember, Skiko is too big. So if I try to change anything of my machine, these values will remain constant, meaning that that is an infinite bus bar. The bus bar is infinite. So now, how do I make the machine to generate real power? Remember, before the synchronization, I use the speed to vary the frequency. Now, after synchronization, if I want real power, I try to increase the speed, that is the speed of the prime mover, and you see the machine generating power. You can see it, and you can even hear it. Now, look at it. It has generated 200 watts. That is 200 per phase. So when you multiply it by 3, that is 600. So the machine is now generated 600 here. We use what? The speed. And you see that the reactive power is very less influenced by the speed. So this is the first thing you have to know. After synchronization, we increase the real power by increasing the prime mover speed. Now, we can also decrease the power by decreasing the speed. And when we try to decrease the speed, the frequency will not decrease because it is tied to an infinite bus bar. So only what will affect will be, it will affect the direction of power to this machine. If we reduce it more, it will become a motor. As we have seen now, it's now a motor. You can see the sound. The sound has changed, meaning that it's now taking power from the supply. But if we increase it, look, first of all, it goes to 0, and then it comes again, it is not generating. You can see the positive power. Now, how do we change the active power? Let me put the real power to 0. How do we change the reactive power? Remember, before we made the synchronization, the field current of the synchronous machine, we use it to change the voltage. Now that it is synchronized, at this point, Q is 0. This is called perfect synchronization. So if I try to increase the field current above the perfect point, that is called over-excitation. When I do that, the reactive power will change. The frequency cannot, the voltage cannot change because it is an infinite bar. So you see that the reactive power Q is changing, and this is 200 reactive power. You can see it's positive, meaning that it is generating reactive power into the system. Q, look at this Q, and look at this positive, it is generating reactive power. That is over-excited. That means I excited over the optimal excitation when it was floating. If I reduce it again, it will come to optimum. You can see it, the reactive power is reducing because I'm reducing the field current until it comes to a 0. This is the optimal. If I reduce it further, this is called under excitation because I'm reducing. Now you see that the reactive is increasing again, but in a negative direction. You can see the negative putting in, meaning that now the synchronous machine is absorbing reactive power from the supply. But look at the field, the real power is still 0. The real power is not affected by the field. So let us repeat it again. After synchronization, we use the field current to control the reactive power. The perfect synchronization point is the optimum. If we increase it above that, that is called over-excitation. The machine will deliver reactive power into the system. If we reduce it below the optimum, that is under excitation, it will take reactive power from the system. Now, there is some time that in that synchronous machine is used in improving power. So, we'll stop here. This is the idea of the machine, the test. Okay, Salaam alaikum.